In the following, we'll show you how conformal mapping provides a map of noise radiation directly on the actual geometry of an arbitrarily shaped object, which in this case is the center console of this car. Conformal maps provide the most easy to understand documentation of the behavior of a noise source. Seeing noise radiation directly on the source surface requires no interpretation and is therefore immediately understood also by non-acousticians. Conformal maps provide better resolution. When noise radiation is calculated at the actual source surface, no loss of resolution due to propagation through the air is experienced. The source geometry may come from an existing CAD model of the surface or digitized using a positioning system, as we'll do here. During digitizing, points are collected on the surface of the object we want to investigate. The model may be as coarse or as detailed as required. The operator simply moves the pointer mounted on the array handle from point to point and collects its 3D coordinates. In this way, a complete set of points on the object is collected. During digitizing, the points may be connected into curves that will later be used to create the surface model. After digitizing, additional curves may be added. Surfaces are created based on the curves, and we are ready for the next step in the process: measurement of the acoustic data. First, we make an overview of the source using the real-time map monitor function. This shows exponentially averaged maps that are continuously updated. By moving the array across the source, we get a first impression of where it's necessary to take measurements. Note that during movement, the position of the array is automatically tracked relative to the geometry. Then we switch to linear averaged mode to take the patch measurements to be used in the final calculation. Patches can be taken at any accessible position, distance and angle, but must cover the entire area of interest. Now the instantaneous array position is shown, together with the position of patches already taken. In that way, it's possible to see where additional measurements are needed. We have now finished, and all our measurements are stored in the database, together with the geometry. Calculation of the conformal noise map can now be done on the spot, or the data can be recalled later back in the office. Here we've started the conformal mapping post-processing software and found our data using the metadata we entered during measurements. We add a calculation of conformal sonar. Before we can start our calculations, we first generate a mesh. The mesh model is generated from the surface model created during measurement. Meshing parameters may be set to suit the frequency range and resolution required. We give a name to the new mesh. We may choose to mesh the entire surface model or only the parts relevant for the particular analysis. When calculated, the mesh model is shown here. The frequency analysis may be either 1/3 octaves or narrow band. In the sonar setup, we may choose the result function: sound intensity, sound pressure, or particle velocity. For source identification, we'll normally choose intensity. Typical calculations last a few minutes, and when they have finished, we can switch to the results window. We can rotate the map to inspect it from different angles, and we can change the frequency range we want to look at. Sound power contribution analysis may be done by defining color-coded areas around the dominating sources. Additional displays may be created and aligned to make side-by-side comparisons between measurements or to inspect different frequencies from the same measurement. To summarize, conformal maps are easy to understand. They provide optimal resolution, and they're even easy to make.